So I want to introduce Elizabeth Barnes at CSU. She's our second keynote speaker for the day and kind of one of my go-to examples of where I think machine learning should be going for applications. So I think we're pretty excited to have her come give a talk on interpretable machine learning for climate science. Go ahead.
Great. Okay, thank you, everybody. And for those of you, I've been sort of doing my rounds like Amy the past few months. For those of you that have seen some of this already, I apologize, but I'm going to assume you haven't and take it from there. So this is work done with many, many people, many of whom are my wonderful graduate students. I won't go through everyone, but I just want to point out that this is really a team effort, not just within climate scientists, but also with those in computer science as well. And as Amy already mentioned, I am also part of AI2ES, specifically thinking about the subseasonal prediction part and the interpretable and explainable AI. And I'll touch a little bit on those ideas now. All right, so I guess I'd like to, even though this is a machine learning workshop, I just like to remind everybody that in my view as scientists, it's our jobs to sift through piles and piles of data and try to extract useful relationships that apply elsewhere. And this is really this idea of relationships that apply out of sample. But as scientists, what we really mean by this is things that are governed by physical laws and equations that we understand that should apply no matter, say, where you are in the world. Some relationship in Africa shouldn't change if you go over to South America. And in many ways, this is what many machine learning methods truly are designed to do, which is help us find these relationships in data. With that said, though, many scientists, we really see this as data goes into a black box and magic happens and some prediction comes out on the other side. And we hope that prediction is useful and right most of the time, and then we can move on. And this in essence can happen because of the complexity and the nonlinearities of the network. And it can learn different pathways of predictable behavior. So I'm speaking specifically here about supervised learning through neural networks, for example. But the big question, and the question as scientists that we're always asking, is why? We rarely just are making a prediction for prediction's sake. We want to know why it was able to do that, whether we're fitting a line, whether we're just measuring data on a field campaign, or whether we're using machine learning. So what did it learn? And I guess one point that's already been pointed out many times already today is just the point that these tools can be interpreted in some ways or another, or they need to be for us to be able to use them for science and for them to be trustworthy. And I guess my message today at all else being equal is just that these tools are no longer black boxes. There are tools coming out right now, honestly, weekly from the computer science community on how we can sort of open this black box and peer inside. And in my view, this is a game changer for our use of these methods for science. And I have heard recently someone said, oh, people use the phrase game changer too often. And I'm going to say, all right, if I only get to use it once, I'm going to use it here. I truly think that now we can talk about using these methods to do science and ask why. All right, so what types of tools are there out there? Well, there are really two sorts of visualization tools, and this is a slide made by my collaborator, Emma Ebert-Uphoff. So there are two ways of thinking about it. Type A, feature visualization. So imagine you have a neural network here, you have some input layer in the yellow, output in the red, and your hidden layers are in the blue. Feature visualization looks to go inside the network and understand all those internal components. So for example, here, trying to understand each of those hidden units. In the case of a convolutional neural network, I might be trying to understand each of those separate kernels. So you want to understand each piece separately. That's one type. This is not the type that my group and I are using the most right now. Instead, we are using type B, which is attribution, or the tools to explain the decision-making process of a neural network. So you want to understand in this type, you want to understand the entire decision-making process. For example, how did the neural network get from the yellows, those inputs, to the output in red? Keeping in mind that, yes, the blue parts are important, but we don't want to necessarily understand each individual component, and we're not going to worry about them, at least for now. We want to understand the decision-making of the entire algorithm. So the particular tool that my group is using, and Scott mentioned it earlier, is layer-wise relevance propagation. This is not, I want to point out, the end-all be-all in my mind. I've already, in the last 2 weeks, had 2 new methods come through my path that my group is looking into now. But this one is a flavor of method that we are finding really intuitive, being trained as climate scientists. It's not only intuitive, but it's relatively straightforward to use, and we see hopes of expanding it to be even more useful for our community. So how does this tool work? So imagine you have a neural network and it's set up to do something with cats, like all computer scientists love cats, it seems. And we have some image of a cat go through the network, and the neural network predicts the probability, for example, that there's a cat in this image. And let's say it comes up with a number of 0.8. Okay, so 0.8, great. What LRP, or layer-wise relevance propagation, does is it takes that 0.8 and it propagates it back through the network and ultimately creates a heat map showing the regions that were most relevant in the input for giving the 0.8 output. Now, one of the neat things about this particular tool is it is, under certain conditions, conservative. That is, if you sum up all the values in that heat map on the left-hand side, so that red blotchy picture, they should add up to 0.8. So it's in essence a way of thinking about where did the 0.8 come from? Keeping in mind, this is a complex and nonlinear network. This isn't just a regression coefficient map. So again, the idea is you have some input, the neural network outputs its prediction, and then you create a heat map in the flavor of that input, asking or to answer where the network looked to determine it was a cat. All right, so what does that mean for earth science research? What does that mean for us? A few things, actually. One, and Amy talked a lot about these different ways of thinking about interpretable, explainable, trustworthy, robust AI. One is for identifying problematic strategies. So getting the right answer for the wrong reason, or another way, we think that our network is doing a good job, but in essence, it's breaking all of the laws of physics. This method could help you figure that out, and that maybe you want to explore something else or find a way to include physics into the problem. It can help you design the machine learning methodology. Perhaps you know that when you're trying to identify bubbling clouds in an image, that the bubbling or try to identify convecting clouds, the bubbling feature is something important because as humans, we know that is indicative of convection. And maybe you see through this method that your machine learning algorithm is not focused on that attribute, then you may design your algorithm slightly differently in hopes of bringing that out of the inputs or out of the data. Another example is building trust. This is a very different type of problem my group is working on, but I thought I would point it out. We're using Landsat imagery to quantify the amount of human activity on the land surface. The left-hand picture here is Landsat from the year 2000, and on the right is the year 2018. And our CNN, our convolutional neural network, has predicted that human activity has nearly doubled over those years, and I can talk more about what that metric means. But we then use LRP in the bottom right-hand corner to ask, why does the network think that humans are making a bigger impact on this landscape in 2018? And we see indeed it's because the network in the red is picking up this large highway that went in 2018 actually. So this gives us trust in the decision-making process of the network. But finally, what I want to talk about in my last few minutes here is discovering new science, that when our machine learning method is capable of making an accurate prediction, we can actually now explore why. So we're doing this for multiple types of topics in my group, but I'm going to talk about two quickly today. This is sort of the Sean's outline version here. So subseasonal to decadal predictability, and then thinking about forced climate change. So here's a very simple problem, but again, my hope from this talk is that you see hopefully the utility of these methods rather than I convince you of some amazing scientific result. So seasonal prediction. So let's say we want to predict the temperature in Seattle in out 3 or 4 months. And for this simple problem, we're going to predict the likelihood that the temperature is either negative, anomalously cold, or anomalously warm. So relatively easy classification in this case. And we're going to use as input sea surface temperatures 3 to 4 months before that time. So we set up our network and it goes through and we can make up predictions. And this is using data from the COVI V2 data set, so 1950 to 2019. So we've trained our network, great. But now we can go back and say, all right, let's look at when it was accurate, when it got the temperature anomalies right on these seasonal timescales. We can then use LRP to ask, where did the network look in sea surface temperature to accurately predict the temperature, the surface temperature in Seattle? And in this case, on the left and the right are two different maps. So one of the things with LRP is it can give you a different heat map for every prediction made. So we can ask, on the left-hand side, we see that again, the tropics and the Eastern Pacific tend to be the most important regions or the most relevant for this network's prediction. But on the right-hand side, same setup, same network, but in this particular input, the network has deemed the coast off the coast of Japan as also being an important region for its prediction. So for us in these applications, the science is not just making the prediction, it's identifying the predictable patterns and regimes of the Earth system. And that's really the science side, is now we can go and explore the mechanisms that may be leading to this predictability. Now, another thing that we're doing with this is we can go in and say, all right, of the network's correct predictions, let's look at the 10% most confident predictions. In this case, these are 73. There are 73 of these cases. And we can make an average heat map of, on average, where does the network look for the 10% most confident predictions. So we get a summary sort of the mechanisms that may be important for predictability on these timescales. In addition, I will point out, as the network becomes more confident, our accuracy also increases. So you might think that, well, seasonal prediction we know is a difficult problem. I would say prediction on any time scale, it seems hard. But on average, our network is 64% accurate with a baseline of 50%, since we're just guessing above or below zero anomaly. But when we look at the 10% most confident, we go up to 82% accurate. So then the question is, what are these opportunities that are more predictable than others? And can we explore them physically to understand the mechanisms? All right, so the other application is thinking about forced climate change and patterns or indicator patterns of forced change. So this is a very different problem. So we're going to think about climate change here in the 21st century as a signal to noise problem. And here is a plot of recent present day surface temperature trends. We see blue blobs, we see red blobs, we see yellowish blobs. And the big question, of course, is when we look at just observed present day trends, how can we tell which changes are signal or are forced responses to, say, anthropogenic greenhouse gases and aerosols, and which are just noise of the climate system? So this is really where my bread and butter in past research is really thinking about climate variability. So how do we do that when we look at one Earth system? Climate models, of course, are great, but when the climate models aren't quite right or they have biases, this becomes really hard to do. All right, so what we're going to do here is we're going to train a neural network to predict the year of a map from a climate model. So we're going to start with climate models here. And this sounds really silly, and to be honest, it is really silly, because my joke is always, no one needs to tell me it's 2020, I already know. So the whole idea here is not going to actually be the prediction, but is again going to be asking why the network was able to make the prediction. So bear with me if you think this sounds a little mundane. So what we're going to do is we're going to take maps of annual mean surface temperature from CMIP5 climate models, and we are going to train a network. In this case, we set it up as classification, wolf fuzzy classification, and I'm happy to talk more about that later because I saw some questions in the chat about regression versus classification. But we're going to ask it to predict, in this case, somewhat the decade that this map is from. Now, if you just think about it, how could you know if a map was, say, from 1920 versus 2020 versus 2100? And the way you'd probably think about it is, well, I know as we go further on in the decades, the globe is getting hotter and hotter and hotter. So I'd probably look for warmer temperatures over, in certain regions. And so the idea is we're hoping the network can look for patterns that indicate the forced change going on in the different decades. The question then, of course, is can it do it? And the answer is yes. So the grade, so what's shown here is the actual year of the map is on the x-axis. The year predicted by our trained neural network is on the y-axis. The gray dots are the climate models we used for training. And the colored dots are actually climate models, entire climate models we set aside for testing. So the neural network was not trained on a set of these climate models. And as you can see, the colored dots generally lie on top of the gray dots and generally lie along the one-to-one line, meaning that the predictions are relatively good. So one thing to note is that in the early decades, the predictions are terrible. The neural network pretty much just guesses 1940 or 1950 the entire time. And this is not some issue if you look of our activation function, or one person asked me if this was ReLU. But actually, I think this is physical. This is telling us that in the early decades, the network just cannot find robust or reliable indicators of change. That is, the signal is weak compared to the climate noise. And so it has no idea what year it is, so I guess it's 1950. And it isn't until about the 1960s that the network is able to find these robust patterns and predict the year more accurately. Now, one fun thing that you can do is so far we've only trained on climate models, and we know climate models are wonderful, but they certainly have systematic biases and issues that may not relate to the real world. So while we can't train on observations because we don't have enough years, if you will, to do that, we need more than one 1980. But what we can do is, now that we've trained our network, we can input observed maps of surface temperature and ask, what year do you think it is? And those are the results are shown in the white circles. And the idea is here that the neural network must be learning things from the climate models that are relevant to the real world, or else it would never be able to guess the year from observed maps of surface temperature. And so again, this is just showing how maybe we can use these networks to combine information from models and observations. All right, so I'm predicting the year. This is pretty darn boring. So let's use LRP now to look for new science, or to look for indicators of climate change. So once again, here's our network set up, but now we can use the concept of LRP to propagate the predictions back through the network and create heat maps that show the most relevant regions for predicting the year. That is, what are these indicator patterns that told the network what year it was? And as an example, these are the types of maps you can make. This is a set of heat maps for the year 2015. So these were the most relevant regions for the network's prediction of 2015. You can see the regions that pop out are really the Southern Ocean, Eastern Asia, and the North Atlantic. Now, you don't have to just do this for 2015. And because this network's nonlinear, these patterns can change with the decade. For example, ozone depletion and recovery has a different timing than greenhouse gases versus anthropogenic aerosol forcing. So we can make maps like this for multiple decades. I don't have time to go into a lot of these details, but a few things to point out. First of all, we know that Arctic amplification is a very large signal of climate change, but while the warming is large, the noise in the Arctic is also large, and climate models disagree. And for this reason, you'll note that the Arctic is not a very relevant region for the network's determination of the year. On the other hand, the East Asian signal has been really interesting. We're pretty sure this is picking up aerosol forcing in this region, because in later decades it becomes less important as other regions become more relevant. All right, so you can do this also, I should point out, for the observations, and I don't have time to do that, but I'm happy to talk about it. And we can actually ask where the network is looking to determine the year from observed maps of temperature. And in that case, the Southern Ocean, as an example, really pops out as an important region. We've also done this for things other than surface temperature, which one could argue is the easiest of the variables we could have chosen. So we've done it for precipitation as well, and are exploring other extremes right now. So in my wrap up, my big picture here, I think that as climate scientists, we're really well equipped to think about this architecture because we love regression. And in many ways, this is nonlinear regression at its simplest. They really are not black boxes. And I think the fact that tools exist to help visualize their decisions is, as I said, a game changer. But we also, as scientists, need to help develop these new tools that are specifically for our applications. And while we can certainly incorporate science and physical constraints, I think my big message here is science can be what the network learns. Because we have these visualization and interpretability tools, we can start framing these networks in a way such that maybe the prediction is not that interesting, but it's the why that becomes the science. And so I'm having a lot of fun with my group because I feel like sort of the kid in the candy store. We're getting really creative and having a lot of fun. All right, thank you.
Great, great talk. I'll go through a few questions when I have a ton of time. We have a little. For the seasonal prediction, how different is the LRP heat map different than the map of the linear correlation coefficient, for instance, between Seattle and SST?
Yeah, I mean, they have a lot of similarities as you would expect, but in terms of linear correlations, that's one map total. You'd only get one map, whereas LRP actually brings out the differences in predictions. So you can actually start to see where one particular prediction may be focused more on the ENSO region and others focused more on the coast off the coast of Japan.
And then global temperature this entire year is in general predictable by knowing ENSO state. It's a novelty that GISTEMP does each year. How is this different?
Say that again.
global temperature this entire year is in general predictable by knowing ENSO state. It's the novelty that GISTEMP does each year. How is this different?
Well, I'd have to find the question again, but it sounds like you're getting at the global mean temperature. A few things is we're trying to predict the year across many different climate models. And so what ENSO is doing in each of them is actually not a big indicator of the year, because 1984, for example, in one climate model could be an El Nino, the other a La Nina. So this would not be terribly helpful in predicting the year. With that said, though, the more interesting problem that I didn't have a chance to show you is when we subtract the global mean from every single map. So the neural network cannot use the global mean at all, but instead must focus on regional patterns, in which case it actually does still quite well. And so we know it's not just picking up on the global mean temperature.
Okay, great. If there are some other questions in the chat, I would encourage you to go through and answer as well. I think we'll probably move on to the next speaker. And I want to thank you again for kind of a great talk.
Yeah, no problem.